So neon, of course, it's a noble gas. We said that these were unreactive, and so it's unreactive since it has its 2p shell filled up. So neon, let's go ahead and write the full electron configuration. So we always start at our 1s. So fill up my 1s, then 2s2, 2p6. That gives me 10 total electrons, which we were expecting since it's atomic number 10. Of course, 8 valence electrons. And of course, if we were to write the Lewis dot structure for fun, we would show again why neon is inert. So neon, 8 electrons, so technically you want to fill up 2 in the S first, then fill up our 6. So 1, 2, 3, 4, 5, 6 in the P. So this gives us 8 valence electrons. So again, we call this, that has a full octet. So meaning it's satisfied. It's not looking to make other bonds, right? It has its orbitals all filled up. So now let's look over at the periodic table and kind of continue. And so, as you're probably starting to feel, this is going to get slightly tedious as we go, down in the rows, right? Writing the 1s2, 2s2 every time. And so I always make jokes that chemists are lazy. We like shorthands. What can I say? And so the shorthand electron configuration is, so now let's look at sodium. So we're looking at sodium. We're trying to determine how we're going to write its electron configuration. And the shorthand method is to start with the noble gas that is previous and then go from there. So that's why we did neon. So neon is our last noble gas that we did. So you could also start with helium, but that doesn't save you much time. But neon starts to save us time. So our electron configuration for sodium, let me switch pens. So now I'm going to start with neon. You write it like so to signify electron configuration of neon. And then starting at neon, so now this is our next shell, n equals 3. So this would be 3s1. And of course, just like we were expecting for our group 1 alkali metals, it has 1 valence electron. And of course, you could always write it the longhand way. I'll just write it for now, just to show. So 1s2, 2s2, 2p6, 3s1. Then I'll go ahead, just for clarity, write our Lewis dot structure for sodium. So of course it would just be Na, the dot here. Again, very similar to lithium, right? It all makes sense. They're in the same family. So they're just different shells. So now let's skip over. Let's do sulfur. So we're just going along the periodic table, filling it up. All right, so this is 3s1, 3s2. Now this is starts the 3p. So 3p1, 3p2, 3p3, 3p4 for sulfur. So I'm just going to write sulfur's electron configuration. So I'm going to be lazy and start with neon. So starting with neon, 3s2. Oh. And then 3p, again, 1, 2, 3, 4 for sulfur. Oops. So it's Lewis dot structure. So how many valence electrons does sulfur have again? 6, exactly. So 2 in the S, 4 from the P, so 6 valence electrons. And again, that matches with that number. So 6 matches the 6A here. So don't forget, right, our smelly family, they all have 6 valence electrons. So let's write our Lewis dot structure. Because again, this is another, at least I think it's powerful. So writing our sulfur. So I'm going to start, again, filling up the S orbitals first. Now I need to fill in 4 P electrons. So 1, 2, 3, 4. So now just looking at this Lewis dot structure, how many bonds do you think sulfur can make? 2. Exactly. Excellent job. So now, right, all the pieces are starting to come together slowly. So we know, right, we have these 2 lone electrons here. So wants to make 2 bonds. Notice how this is similar to oxygen, right? So they're the same family. So you can imagine that the same thing applies to oxygen, right? It wants to make 2 bonds. So now the valence electrons for this one, again, they're just the ones on the outermost shell. So now that we've moved down to sulfur, so we're on our 3rd row here. So now all I care about are those outermost electrons on this 3rd shell as we started our 3rd shell. So that means for sulfur, that includes our 3s2, since again this is the outermost shell here, our main shell, and then also includes our 3p. And then the valence electrons too should match with these numbers up here. So if you're ever confused, that's why we have our periodic table as a guide here. So that's why it has this little 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. All these match with the number of valence electrons. Does that clarify that? Yeah, so like all these, right, have one valence electron. It's just their shell number keeps increasing. So you kind of have to think about it as an onion ring too. And again, just follow these big numbers to kind of keep you straight over which, kind of onion ring layer you're on. What happened to my periodic table? There it is. And so it's easiest to see with the alkali earth metals, hence why I kind of keep going back to them. But we started with hydrogen, and so notice it's just like one big red ball, right? Because that's just signifying our first shell. Then we go down to lithium. So notice right now that red circle's kind of in the center here, in the core, so kind of buried, right? So now we're not even looking at the 1s2 anymore. And so our valence electrons for lithium is a 2s1. Go down to sodium. Now it's 3s1. And again, now we just keep adding our onion rings. So we have, you can still see our S deep in there. So our 1s, 2s, now our 3s. We keep going. And you just keep adding, right, onion ring shells. And so that's why we only care about that last N equals, or excuse me, that's why we care about the outermost shell. So this is just ptable.com. So it's just a simple periodic table, interactive. And again, this is why I like it, because now let's take a look at cesium. Let me try to zoom in on this. Oh, it doesn't work the greatest. So you might have to check this out on your own computer to kind of see the electrons a little better. But if we're looking at cesium, yeah, I like it. So it tells you, so not only does it tell you, right, the electron configuration here to help you. Hey. Oh, my cat's being bad. He wants attention. But anyway, sorry. So cesium, right, it tells you the electron configuration, but why I like this periodic table is it also shows you all those electrons filled in. And so kind of going back to these valence electrons, right, cesium is on this 6 n equals 6 level. So all these inner electrons here, right, these are all core electrons. And so we don't care. It's not that we don't care, but it's just that they're not influential, right? Because they're deep inside here. Yeah. As everything. And so it's a little bit harder to see with the p orbitals, obviously, but it's kind of the same. Yeah, you can't even see the onion rings, but basically right there, p orbitals kind of in onion ring form as well. So it's, oh, there you can kind of see it with thallium. So again, we're only caring about the valence electrons. So in this case, we might have to do some numbering, right? So this is 2p, 3p, 4p, 5p, 6p. So that matches with this row here. So we know thallium's valence electrons are going to be located in 6p, then 1, because I'm just looking at this 1 here. And that matches with its electron configuration. So we'll go over how to find this complicated electron configuration. But right now I'm just trying to show that that's how we get the valence electrons. And then there's our other p orbitals kind of buried in there. So before we jump around too much, Let's continue filling it in order. And we're about to have a little bit of maybe confusion. So we have 3p, and so we finish off the 3p, right? So argon has 3p6. So now we filled up that. Now this continues with n equals 4. So back to our S block. But now what is this? So let's stop for a second. Let's go back to our kind of shell models. So we had started with n equals 1 that only had s orbitals. So there were 2 electrons in that. Then we filled up our n equals 2. And so if the s orbital had 2 plus 6 from our p, this means we have 8 electrons in our second shell, or max of 8. So now as we go to the n equals 3 shell, we can have s orbitals, we can have p orbitals, but now we're introducing our first d orbital in there. And so these d orbitals, let's look at them. So there are 5 d orbitals. So each d orbital holds 2 electrons. So they each hold 2 electrons. And so there's 5 of them. So that means there's 10 d electrons total. Going back, again, if you've taken kind of high school chemistry, you may have seen this like 2, 8, 18 pattern. So this is where it's derived from. So now in our n equals 3, the s contributes 2, plus 6 from the p, plus 10 from the d. That gives us 18 total electrons in this n equals 3 shell. And so why I wanted to stop and do this is so that we don't forget when we do our periodic table and we're going in order, this is actually 3D. So write that, whatever you need to know, star it. This is 3D. So even though we went to 4S, now we have to go back and fill up 3D. And so notice, right, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across. So this is our D block. So you probably want to highlight this. D block. And so let's do nickel, the electron configuration for nickel. We'll do that together. And so we will not write Lewis dot structures for transition metals, just because, again, I think I mentioned this, that transition metals, they do a lot of funny things. And so, Lewis dot structures wouldn't be really reflective of their activity, actually. So let's do the electron configuration, though. So I'm going to start with argon, since argon is my previous noble gas, and it's starting to become a lot to write all this down explicitly. So we start with argon. Now I'm going to go back to my periodic table to help me fill it. So argon. Now we go back to our S block. So 4s2, right? 4s2. And then now we need to go back to 3D. So 3D 1, 2, 3, 4, 5, 6, 7, 8. So 3D8 there. And so that matches with what we